with me is Adnan, and we're here to present a paper on the economics of natural resource scarcity, the state of the debate. Now, Professor Kramer in his paper introduces a few key questions. Can economic growth be sustained in a finite natural world? Can human ingenuity combat the depletion of natural resource commodities? And how should humans measure and preserve natural resource amenities? Now, the debate begins with Malthus, who was a bit of a pessimist. He predicted that exponential population growth and the diminishing marginal product of capital and labor would eventually cause resources to run out. Now, Malthus did not foresee the Industrial Revolution nor the technological developments that came after, but his general line of thinking has influenced many thinkers in the 19th and 20th centuries, such as Stanley Jevons, who in 1865 predicted that the cost of coal would increase due to scarcity, and since coal fueled the British economy, it would undermine economic growth. Additionally, the conservation movement in America focused on preserving a broad range of natural resources and keeping their management in the hands of scientists. Finally, post-World War II growth also spurred another wave of concern over resources, particularly in the wake of the Cold War. This led to the birth of Resources for the Future, a research organization which examined empirical evidence for scarcity in their first publication, Scarcity and Growth, in 1963, which supported generally decreasing scarcity between 1870 and 1958. Another volume was released in 1979 after the environmental issues and the OPEC crisis in the 1970s. And this report was also cautiously optimistic about resource commodities, but also mentioned resource amenities as a source of concern, which we will define as the generally non-market environmental services that the Earth provides, such as fresh air, the climate, ecosystems, recreation, etc. Now, there's been a much greater focus on amenities since the 1980s, and the current debate on sustainability is heavily related to resource amenities.
So as we previously defined resource amenities and established, they kind of like, our playgrounds where we recreate goods and services and observe the market conditions. So John Critella's seminal paper in 1967, she highlights a new focus. She makes an argument that technology is more able to provide substitutes for resource commodities than for resource amenities. So as a result, the relative value of these resource amenities would increase over time. This in turn has important implications for development decisions, mainly when future values were uncertain and the loss of preserved environments was irreversible. So it is quite intuitive that economic activities from the extraction of resource inputs to the emission of wastes do damage resource amenities. Take the dams and water diversion projects, for example, that provide water for irrigating crops. However, upstream water withdrawals from irrigation reduce the water available downstream, which results in disastrous effects. Take the Aral Sea, for example, whose volume dropped massively before the 1990s as a result of irrigation diversions. 20 out of the existing 24 fish species in the lake disappeared as a result. So it is quite difficult to imagine any extractive use of natural resources that does not in some way affect natural resource amenities. So the question remains, why is it so hard to pinpoint these damages on resource amenities? So part of the answer to that question is that the ecosystem is very well interlinked and very well connected. Commercial exploitation of natural resource commodities generally considers at most a few of the elements of the ecosystem. But on the other hand, resource amenities is it's very well drawn and, all the elements of the ecosystems are considered. So therefore, it's very hard to pin out the connection due to the complexity, and therefore there's a lot of uncertainty. This complexity raises important questions about how property rights can be assigned and how all of the externalities of commercial exploitation can be internalized when some of them may have not even been identified in advance. So as we learned early on in the course that natural resources that provide these amenities are often open access resources, and many of these goods and services are public goods. So therefore resource amenities do present significant management challenges for social institutions. The interdependence between natural resource commodities and amenities implies that natural resource and environmental policies cannot be concerned with a single resource or single resources, and they have to be looked at as complete ecosystems and indeed be treated as the environment or as a whole. So as for the empirical considerations, it is imperative to understand that there exists this constant race between technological progress and diminishing marginal returns in a world with finite natural resources. The prospects for future generations depends upon which trend is proceeding at a fast pace. Many issues then boil down to a seemingly simple empirical question of whether technological progress can overcome diminishing marginal returns. the substitution of capital, and technological progress in resource extraction and commodity production have led to generally downward sloping price trends for many natural resource commodities. If there's any systematic bias to past predictions about the future, it is definitely an underestimation on the ability of technological progress to overcome the scarcity. For example, petroleum supply forecasts have always overestimated the future price of oil and always underestimated oil production. So, in general, the empirical evidence to date for natural resource commodities is largely in favor of technological progress. So we have three economical variables that measures and have been used as indicators of resource scarcity. There's extracted resource price, marginal extraction cost, and user cost. Extracted resource price is denoted by the letter P, extraction cost is by C, and the user cost is denoted by lambda. And these three indicators are very well connected and related through a basic first order condition. And if you solve for that, that'll give you the optimal resource extraction. So the user cost very effectively captures the non-extractive economic cost of current depletion, including the foregone regeneration for a renewable resource and the foregone future use of a non-renewable resource. So it pretty much captures all the concerning future variables. It's kind of like depreciation of a resource. Extraction cost is computed as the amount of labor and capital needed to produce a unit of output. Extraction cost is founded on the classical economic view that with diminishing marginal returns and finite natural resources, the cost of natural resources should generally increase as demand increases and depletion occurs. The tendency towards increasing extraction costs can definitely be offset by technological progress. The cost measure for agricultural production actually declines more rapidly after the 1920s, even though agricultural output increased four times over the same period. Within the same period, also, the economy became very mineral intensive as mineral use increased about 40x. However, the unit extraction cost for minerals significantly declined. So as you can tell, the data does not support the strong scarcity hypothesis of increasing scarcity. Um, so let's reconsider scarcity and growth. And however, the results are the same. All major sectors continue to show a strong decline in labor per unit extracted cost. So why is this cost decreasing? And also there was an outlier in US coal extraction costs, which generally increased. But however, this could be due to other economical variables, like they could have exercised their market power rather than changes in the scarcity. So many economists viewed environmental impacts as a more significant concern than increasing scarcity. So for example, in the 1980s, an aggressive pollution abatement policy costed about 3% of the output, which reduced projected annual economic growth by less than 0.1%. Which makes you actually think, are these policies actually aggressive, or can we be more aggressive? So on the right here, you can see the declining extraction costs over the years in different industries, and some of this decline in labor and capital costs per unit of output that we see here could have occurred because energy was substituted for capital and labor. So that makes you think, is this a good input measure? The author does not believe so. He thinks that there's a lot of shortcomings of using extraction cost as an indicator of resource scarcity. Extraction cost is an inherently static measure, and it does not capture future effects that are more important, and that does not really indicate natural resource scarcity. In addition, extraction cost captures information only about the supply side of the market. So if demand is growing more rapidly than the extraction cost is declining, the extraction cost will give you a false indication of decreasing scarcity. So the other two economic variables that we studied, price and user cost. So they do incorporate information about the demand side of the market, and they, at least to the extent possible, they also give indications about expectations about the future demand and availability. So for this reason, they're generally the preferred indicators and measures for resource scarcity. So, for most of the 20th century, natural resource commodity price trends have generally been flat or decreasing. Since these are non-renewable resources, one might, hypothesize that they would have been more prone to increasing scarcity and increasing prices. However, mineral prices have been declining over the 20th century, as you can see here. See, the price of copper has been declining over the years, even the price of lead, as you can see here on the right. And even in terms of natural gas and petroleum, the price hasn't been quite increasing. It's just, quite fluctuating. And so there is an exception that exists to this downward trend of non-renewable resource prices in the period from 1945 until the 1980s, as you can see here. So over much of this period, many of the non-renewable resource prices showed an upward trend. So this basically seems to match the U-shaped price curve that we've all studied, that occurs as depletion exerts an upward pressure onto the price, and a downward force is exerted by technological progress. So again, coming back to that constant race that I mentioned. So back then, economists thought that non-renewable resource prices would continue to increase, but as we know, the prices did not continue to increase. The economy responds to price increases in various ways. Substitutions are made, resource saving technologies are developed, new reserves are found, new methods for recovering resources or reducing the cost are found, and so on. For example, before grade copper could not have been utilized, but now we have ways to refine that low grade copper and utilize products that were of no use earlier on in the days. So, part of the price declines occurred as some of the environmental externalities associated with resource extraction have been internalized, which has been happening throughout. So, but we see, we have to consider that there is a finite amount of resources, and in this context, oil in the ground, and production cannot increase indefinitely, and it ought to reach a peak and eventually decline to zero. So on the right here, we can see the Herbert curve of oil production. He argued that because of production technology, the relationship between production and time would trace out a bell-shaped curve with a positive exponential growth rate for production in the early years and an exponential decline to zero. The area under the curve would be determined by the amount of recoverable petroleum. So the world production, was predicted to be peaked about in the 1990s or 2000, and technological developments have increased the recovery and more exploitation of oil from the existing reserves. So we can probably tell, from our talk with Dr. Yazdi earlier this month, that there are so many different ways now to extract oil. So as a result, the actual production has not really followed this bell-shaped curve that he predicted. So other major natural resource sectors show increasing productivity and declining prices. Mathis's prediction about population and food supply was inaccurate. Food production has exceeded population growth. For much of the last 2 centuries, the increase in food production was the result of bringing in more land under cultivation and farming existing land more intensively. The increase in agricultural productivity has increased food availability and lowered the prices. So as you can see here, there's these selected food commodity prices, and you can observe a decreasing trend over the years.
So the empirical considerations around resource amenities are harder to measure, as amenities are non-market and they are unable to be physically measured in most cases. As a result, it's harder to evaluate the empirical concerns. We've had some successes in the past few decades before the turn of the millennium, particularly in the US and Europe, with air quality and water quality. However, the overall outlook is still quite concerning, and the paper goes into a broad survey of some key issues around these amenities. Starting with land conversion and degradation, where 40 to 50% of the land converted or degraded by humans, and just over half of forest land still exists, and there are 6,000 threatened tree species, among other amenities that the forest lands provide, such as habitats, controlling runoff water, holding soil together, etc. Finally, forest lands are a good measure of biodiversity, which is commonly measured through loss of habitat, actually, because it's a bit difficult to measure otherwise. And biodiversity loss has been 100 to 1,000 times the natural rate of species loss. Now, another big issue here is climate change, which we've talked about extensively in this class. Climate change is mostly as a result of greenhouse gases, and it will damage a variety of habitats and climates, such as Alaska, where the freezing point of water is relatively close to the year-round temperature. As a result, permafrost is melting, infrastructure is being damaged, the ice is thinning to destroy habitats, for example. Another source of concern is coral reefs, as an example, where coral reefs are very sensitive to climate change as well, and even a small change in the average temperature will irreparably damage them. Of note, this is a significantly larger issue today compared to 2005. As you can see, the atmospheric CO2 is still going up despite commitments otherwise. Now, to empirically measure these resource amenities, World Resources 2000-2001 is a report on 5 ecosystems: agricultural, coastal, forest, freshwater, and grasslands, on their ability to provide 8 essential services: food and fiber, water quantity, water quality, biodiversity, carbon storage, shoreline protection, wood fuel, and recreation. Out of these 40 possible categories, 24 were able to be assessed, and the results were, well, they were mixed. 6 were good, 12 fair, 5 poor, and 1 bad. More concerning, however, is that 18 out of these 24 categories are declining. And so overall, there are signs of concern that environmental amenities are declining. So, more theoretical considerations, we must make a distinction between commodities versus amenities. In commodity scarcity, price signals will trigger responses to alleviate the scarcity. Amenities, on the other hand, do not have such price signals attached, and therefore collective action is more imperative when it comes to resource amenities. Now, is it possible to sustain a growing economy with finite resources? It may be possible theoretically, Professor Krautheimer claims, given capital growth. Now, the key question is, can capital be substituted for a non-renewable resource input? In a growth model containing capital and a non-renewable resource, the key to measuring whether growth can be sustained lies in the elasticity of substitution between capital and the resource, which answers that previous question, because a high elasticity will allow you to more easily substitute capital for the resource. With high enough elasticity, growth is theoretically sustainable infinitely with a finite resource. Examples of elasticity and substitution can be seen in glass panes for insulation, where the glass panes are substituted for whatever heating we use for our homes, like natural gas, for example. The substitution of fiber optics, replacing copper, which is a more scarce resource, for telecommunication uses. And finally, the general reduction in energy costs used to produce $1 of GDP, down 50% from 1949 to 2000. These technological advances are a key reason why commodity scarcity is not increasing. Some implications of the above conclusions are that substitution implies not all resources must be harvested. We can have a natural world with resources unharvested and still sustain our rate of growth and our living standards. The protection of the environment, therefore, should also account for the value of amenities. Finally, however, we should note that substitution cannot occur indefinitely. It is simply not possible to produce infinitely using finite inputs, regardless of capital substitution. So the conclusion is that any permanent solution must rely on renewable resources rather than non-renewable resources. Another big point is the fair treatment of future generations. So do we discount the future generation's utility? When we do, large discount rates can be construed as mistreatment, valuing their utility less than ours. However, equal weighing would require the first generation to make great sacrifices in order to accumulate capital for future generations, which would be unfair to us. Now, considering natural capital, the role of the rate of time preference becomes more complex. Because if you have lower discount rates, for example, it will increase accumulation of natural resources, natural capital. However, indirectly, it can also actually lead to more resource depletion by increasing accumulation in resource-extensive industries, for example. Now, this highlights the key problem around resource amenities, which is typically efficient asset accumulation requires equal marginal rates of return. However, when it comes to resource amenities, most of these returns are social returns. They're non-market. You can't purchase environmental assets the same way you can purchase other assets. As a result, unless this is corrected, unless we find a way to accurately measure the returns of non-market resources, individual investments will favor other assets over environmental assets, and it will eventually deplete these environmental assets. Now, the current line of thinking around a more practical solution would be to set quantity constraints on the use of natural assets. Such quantity constraints can include forest preserves, for example.
As for the summary and conclusion, empirical evidence does not indicate a significant increase in scarcity of natural resource commodities. However, the historical evidence is that expansion into previously undeveloped lands and technological progress have enabled the human economy to avoid the Malthusian trap and to maintain adequate supplies of food, forest, and mineral products even as population and economic output increases substantially. The desire for a higher living standard in the developing world places additional demands on technological progress to prevent increasing scarcity of natural resource commodities. Nonetheless, one can be optimistic as there does not appear to be a significant shortage in the near horizon. The world's economies have not been as adept at preserving natural resource amenities, which is more concerning. The inability to appropriate the benefits of natural resource amenities reduces the incentive for technological developments that could preserve or restore natural ecosystems. Further population and economic growth will increase the ecological pressures. Without significant improvements in technological protection, the further availability of natural resource amenities is in jeopardy. The first step is to correct the institutional failures that result in undervaluation of these goods and services. We are far from understanding how ecosystems function, and the interdependence and connectedness makes it difficult to design simple remedies. These are the list of references that we've used, and thank you very much for your time and attention.